Okay, so we've hit 2 minutes after the hour. We usually wait just a couple of minutes for late joiners, and I know additional people will be joining. So my name is Jim Kurose. I'm a faculty member here at the University of Massachusetts, and we've got a really fabulous networking channel event today on connected spaces, challenges and opportunities in satellite computing and networking. I would have put networking first, but fine, networking and computing, because you'll see our panelists are going to talk quite a lot about both networking uh, and computing. And we've got a really all-star cast of folks here today. You can see them on the screen. We have Debopam Batterjee from MSR in India, Nitinder Mohan from TU Delft in the Netherlands, Nishanth Sastry from the University of Surrey in the UK, and Deepak Vasisht from UIUC here in the United States. And to give you a level of their all-starness, the four of them were involved in a recent workshop that was held at Dogstuhl on this precise topic. And Dogstuhl is a place where you can get together with 50 people out in the woods. There's nothing else to do at Dogstuhl except talk to the people there and talk about research challenges and opportunities. And that's what they're going to be talking about today. So we're really, really pleased. Thank you, all four of you, for being here. I'd say also, Nishanth and Debopam, you were both part of the first networking channel event that we did in Leos. I think it was like 2.5 years ago. So thank you for that. Thank you for today, and welcome back. So here's what the structure of what we're going to do today. Nishanth is going to start off with just a broad overview of Leos networking and computing, and then the four of them will be talking about different aspects about that in more detail. So for the first half hour, talks by our presentations by our four panelists, which will be great. We'll open it up for some conversation and questions, first among the panelists, and then we'll open it up for questions coming from all of the folks sort of around the world in this networking channel event. So for those of you who are able, we'd love to get questions and comments. There's a Q&A part of Zoom down at that bottom where you can enter questions. We may be able to answer some of them online in real time, and others will queue for discussion, starting probably 40 minutes past the hour, something like that. And I'll sort of moderate the questions and pull questions out of the Q&A part that haven't been answered and direct them to the panelists. So without any further ado, and we're going to stop probably just a couple minutes before the hour so we can tell you about the next networking channel event. And so without any further ado, I think what I'd like to do is I'd like to turn the screen over to Nishanth, and he can take it away. It's going to be great. Thanks.
Great. Thanks a lot, Jim, for the invitation. Let me see if I can share my screen. Okay, let me get you guys out of the way. Hide video panel, hide meeting controls. Okay, can you confirm that you can see my screen?
Good.
Yeah, okay. All right, I thought we'd start with a very generic overview of what all the excitement is about in terms of Leo networking in recent days. But the place to start is actually not in recent years, but way back at the beginning of the internet. If you look back at how ARPANET actually expanded outside the US, it turns out that the very first nodes involved satellites, right? So they were talking to two nodes. The first was NORSAR in Sweden. And when they started talking to them, they said, well, we also want to add London as the other node as well. And I have here a picture from what I think is like a cyclostyle thing, a report written by Peter Kirstein. And so my PhD advisor is John Crowcroft. John's PhD advisor is Peter Kirstein. So my academic great grandfather wrote this report, and he wrote this report before I was born, right? So this tells you, and before probably all the panelists here were born. So that tells you like how far back in history we are going. And you'll see here, let me just put on my laser pointer. You'll see here that there's a station at Goonhilly, which then connects to London, and then which turned out to be the first link outside the US. And it turns out that the difficulties of connecting the ARPANET to outside of the USA through the SATNet project was what led to Transmission Control Protocol program, or TCP as we know of it now. And Peter Kirstein together with Windsurf kind of shared the activities to develop packet satellite research. So this is really, really old stuff. So why is there so much excitement about it? Well, if you look at it, satellites come in three different flavors. And essentially, all of them are trying to do exactly the same thing. They're trying to connect me in my house or somewhere in the field to the rest of the internet, right? And these three different flavors are GEO, MEO, and LEO. So Norse are the Intelsat satellite. They're all talking about the geo space, whereas the current excitement through Starlink and others is in the LEO space. So what's really the difference between LEO, MEO, and GEO? So one way to look at it is, so if you're, let's say, on top of a skyscraper, you can see a vast amount beyond what you can see maybe at ground level. So think of Geo as being on top of a skyscraper. Think of Leo as being much more closer to ground level, say the first floor or the second floor, right? Um, and so the advantage of Geo obviously is that because you can see such a large amount of the Earth, you need very few satellites to kind of provide coverage across the globe. About 3 satellites is enough to cover the entire globe. Unfortunately, though, going all the way up and coming back down takes about 250 to 500 milliseconds. And in the end, it was this delay that turned out to be too much for most applications that we wanted over the internet. In LEO, by contrast, we get a latency as low as 30 to 50 milliseconds. But that also means that the LEO satellite, each individual LEO satellite can only see a very small portion of the globe. So you need a lot many more satellites to kind of connect them. So if you remember, some of you might remember the Iridium constellation, which was the very first such constellation in the LEO space. And it was called Iridium because they did some initial calculations that showed that 77 satellites are required to cover the entire globe. And the atomic number of Iridium is 77, right? So they thought of the Earth as being the nucleus in the center, several electrons, LEO satellites like electrons going around the Earth. In the end, if you want to support 9 million subscribers, like what Starlink is trying to do now, you need many more satellites. Starlink now has about 10,000 satellites, nearly 10,000 satellites up in space. So how does connectivity look like? Well, the simplest way is what is known as bent pipe connectivity. There's a user terminal which beams signals up to the satellite, which then reflects it back down to a ground station. And from there, it goes merrily along its way, just like you would in terrestrial internet. Sometimes you may not have a ground station very close by. So constellations like Starlink have what are known as inter-satellite links. So you go from user terminal to satellite, satellite to satellite to satellite until you can come back down to a ground station. Typically, the easier links here are when the inter-satellite links are within the same orbital plane. But you can also have links across orbital planes through so-called plus grid topology. We initially thought that there would be 4 inter-satellite links. In deployed Starlink satellites now, they're saying that there's about 3 laser links rather than 4. So what does this raise as opportunities for us as researchers? Well, instead of having routers being stuck somewhere in a grubby basement, we now have networking equipment which are moving very, very fast at 27,000 kilometers per hour. Which means that every 3 to 6 minutes, you have an entirely new satellites that you might need to connect to. This means that overall, you have a large dynamic network with constantly changing connectivity, and this needs to be managed at scale. And that raises some very interesting topology management, traffic engineering, routing type of problems. And such a large changing dynamic topology also means that we need to rethink many of our end-to-end network protocols, transfer protocols, and so forth. So essentially, we are looking at a redesign or at least a relook at the entire networking stack because of this. There's also many L2 challenges which people cleverer than me work on. I'll just mention a couple of them. One, because of this such high speeds, we have to think of Doppler shifts. Something that we found when we did the first measurement study of Starlink back in 2022 is that weather can play a significant role. So even moderate rain, we found, this was in IMC 2022, we found that even moderate rain can increase latency by up to 2x. So these are things that L2 people also need to worry about, right? So I'll kind of stop there because Nitinder is also going to give us an architectural primer as well. But I want to say a few things before I conclude. One, Leo is not just Starlink. There's a lot of attention to Starlink because Elon Musk is very public about it and because they are currently the market leaders. But there are many, many other players. I'm listing a few of them down there. Second, Leo is not just broadband. So mostly Starlink is looking at broadband, but Starlink is also entering the direct to cell space, which is instead of talking to a user terminal, they talk to a smartphone directly. There's also satellite IoT that people think about. There's a separate set of research looking at remote Earth observation and so forth. But in terms of communication, satellite IoT and direct to cell, apart from broadband, are the main ones to look at. And finally, the networking in space extends way beyond LEO. We talked about GEO as the historical origin, but now people are looking at beyond into deep space as well. NASA Artemis mission wants to introduce 5G connectivity on the moon. Some of you might remember during the DTN wave, there was Kevin Fall and others who set up the Interplanetary Internet SIG or IPN SIG. We also have a new IRTF group called Space RG, which is looking at LEO and beyond. And we are going to have a meeting in the IETF happening in Shenzhen next week as well. So I'll stop there and hand it over to Nitinder for the next step.
Perfect. Thank you so much, Nishanth. Do you see my screen, by the way? Okay, great.
Yep.
Glad to be here. I'm Nitinder. I'm an assistant professor at TU Delft. With these great set of folks, I've been involved in several satellite activities, including LeoNet, a plug coming in later. So I'll build upon what Nishanth just mentioned. So all of the satellite hype that we have gone through in the last almost a decade now, it's nothing new. I mean, most of these operators were proposed or they were doing a lot of these technological advancements back in early 2000s. And they all went bankrupt as well. Even the technologies that they were using for communicating back to the Earth, the Ka, bands, those are still the same technologies. Almost nothing happened in the last 2 decades, which we coined up the term as satellite winter in the Dark Stool seminar. This was because simultaneously there was an expansion in a terrestrial mobile network as well. And people could really see more use cases which were designed to build connectivity on terrestrial networks, higher speeds, whereas the satellite terminals that you were using were bulkier. You had to be outside. They rarely worked. They found their uses mostly in security domains, but they didn't really pick up from a commercial perspective. Now, also building on Nishanth, the Starlink is not the only satellite network that we should be caring about. There are several new popping up. Amazon Leo, OneWeb are the more popular ones. There is, from an EU perspective, Iris Square constellation, which kind of brings multiple parties together. Open Cosmos, for example, like these are all the folks that are trying to also build their satellites and launch them into space. So the traffic up in the space is becoming slightly more denser as we are going further. And this is, to give you a perspective, this is a slide that I picked up from Dan York from ISOC, and he was showing how many constellations are planned in years to come. In 2024, we were looking at almost like 90,000 satellites what people were planning. In about next year, these numbers have gone into the orders of 1 million, 1.7 million mega constellations, large constellations as well. Starlink alone wants to launch like 30,000 plus satellites. And this is an increasing numbers up in space that we're going to see. All for what? So to give you some architectural perspective, and these are the kind of numbers you will see if you start reading papers on LEO satellites. Most of the satellite operators would launch their satellites in different orbits, and essentially orbits are based on the orbital angle that these satellites make to the equator of the Earth. So Starlink, for example, has most of the satellites in these 4 different orbital shells. And why do you want to separate them across multiple orbital angles is because if you flatten the picture of the Earth, no pun intended, you will see that these satellites are covering not only just different areas of the Earth, but they're also then covering like the different areas with a different cadence as well. Most of the populated regions where you see markets are within the 43 and 53-degree angle of the orbital shell, which is why you tend to see most of the satellites also deployed in this domain as well. But what I also want to pitch is that these satellite operators are not just space node operators. They are very much terrestrial network operators as well, because they follow some what we call as a bent pipe connectivity. And from a bent pipe perspective, just to paint a picture is that, okay, you have the Starlink terminal. Now with the direct to device, you also have a phone. You can connect to a satellite. A satellite can directly connect you to a ground station by making a direct bent pipe, or it can use its laser links to offshoot you in its train to get you to a ground station, which is a bit far away. And this is where you are kind of routed to a point of presence where you get an IP address and you're essentially going to browse the internet. So your connectivity is going to be very much dependent upon where your ground station is that you're mapped to. And essentially, this entire connectivity, as these satellites are moving around at 27,000 kilometers per hour, this has to stay stable. The way satellite operators do this is they pretty much just put this entire connection of the bent pipe behind a CG NAT, and they said, okay, this is where magic happens, and you always get to see the connectivity to your point of presence. This is the first node that you will also see in your trace outs. But essentially, this also changes your performance number. So these were the measurements that we did in 2023. This was published in WebConf paper in 2024, where we looked into the global performance of Starlink, comparing it with mobile network operators. And we found that, okay, Starlink has almost 40 to 50 milliseconds of latencies at that point of time. This number has come down slightly in the last couple of years now. But you will see like a lot of discrepancies between regions where you have a dense ground station deployment versus, for example, Africa and Asia, where numbers can be much higher. And this is where, for example, if you compare it with cellular is definitely a winner in this case. And this is why you will see that Starlink and all of these operators are not really, I wouldn't consider them, for example, competitors of your mobile terrestrial operators, but mostly like an extension services, because this is why we also see now, last week, Starlink announced Starlink Mobile at MWC. You have AST Space, for example, which is also trying to do direct to device. But essentially, they want to provide you connectivity where your terrestrial mobile connectivity fails. And you will start to see this as the pitch that most of these operators will make. And yes, I mean, the places where you tend to see more ground stations is also places where you have more customers. No surprises there. Your US and Europe is well provisioned here, Asia not so much. And this is why your latencies can be significantly higher, because you're mapped to a ground station which is farther away, or you tend to see a lot more competition in your connectivities as well. In fact, in a very recent study, we were tracking the CDN performances on these networks. This is published this year in WebConf as well, where we were able to track the ground station deployment in Africa. And this is what we see, that in 2025, in January, Starlink deployed new ground stations and new point of presence in Africa. And you tend to see your latencies kind of reduced by a margin of 2x. Just because you were able to route your connectivity closer to the users and your internet exchange points, which are closer to you. This also improved the user performances as well, because you were now hitting the right CDN servers, which were more caching the contents which were more relevant to you. Okay, so with this, I mean, there were several open challenges still that plague this space. And we had several of these questions that we were trying to answer. And we have the LeoNet. We were trying to answer these questions as well. But in earlier February, we organized this Darkstool seminar. Jim gave a very good overview about what Darkstool seminar is. You are in a secluded castle in Germany, where you are locked in together with the drinks and food, and you get to discuss these topics. There's nothing out there. I'm thankful to my organizers, Nishanth, Paulo, and Brandon, for co-organizing this. We had about 28 participants who participated in the seminar. And in this next set of slides, I'll give a very high overview of what we came up with. Essentially, the idea was that we bring the three different stakeholders within the ecosystem, the academic, the industry, and the policymakers. And we have discussions around several of these topics. The key topics for us was, what does this NTN-TN architecture looks like? What are the various use cases that are relevant for this? What are the interoperability and regulation challenges? Space computing, is it a myth? Or is it going to actually take off? What are the security and resilience problems? We are working on a full report, but to give you a slight knowledge about what we discussed, let's talk about the NTN architecture. So most of the applications that we see so far are mostly focused towards Earth-based application. But here also, as we were discussing, we realized that the space has a lot of variables. You have variety of communication technologies on how different entities within this can cross interact with each other. You can consider, for example, aerial nodes as well, and aerial nodes can have direct connectivity with your satellites. And this is now useful if you're, for example, traveling on an Etihad flight and you have a Starlink connection and you are able to browse or play games at a good ILF connectivity performances. But then again, I mean, you also have them deep space, which has until now been slightly not given that much attention. And this is where also I believe, or what we felt was more attention from research should come in, or will come in the next couple of years. Because if you want to connect, for example, nodes which are cislunar or surrounding Mars, you are interacting at a different set of challenges. Your latencies are no longer in milliseconds, they're in minutes. And then also you need to think about how these nodes can cross interact with each other based on if they have direct line of sight connectivity. Most of our IP protocols do not work here. There is an entire working group dedicated to solving this problem in IETF called TipTop. And they've been making a lot of progress on how we can approach this problem as well. But from an architectural opportunities, what we felt was that there is even if you're looking into Earth-based challenges, in addition to like a low-hanging L2 fruits, like, okay, you want to do link optimizations or connectivity, routing seems to be a problem. We can also think about cross optimizations across not just LEO, but bringing in LEO, MEO, and GEO architectures together. And what we also felt was that there is a lack of simulation and emulation tools that actually gets us to try around all of these different link dynamics. And I think Nishanth is going to go again at the end of this panel to get more insights there. Space computing, a lot of hype around this recently. I won't take a lot of buzz around from Debopam and Deepak, who are going to talk a little bit more on this. But essentially, what we discussed was that we need to think beyond Earth-based applications for compute. I mean, LLMs in space do not make much sense, but deep space computing actually has been a real challenge from the longest time, and folks in NASA and ESA have been dealing with these problems. Your Curiosity rover, for example, is running with a 200 megaflops of compute connectivity. So there is a need that, okay, you can, for example, offload to something which is revolving around in space and do computations there. Compute in deep space, you have now use cases that actually benefit immediately, require low latency for operations. But terrestrial-based space compute also makes sense if you're also thinking about content storage alongside with it. I know the other two panelists here might have a different view on this, so I will completely offload on this. Security challenges. Also, right now, what we discussed was that there are only challenges and not many solutions out there. Most of the solutions are that you come back to Earth and you do Earth-based PKI. And this is also an open research problem where you can actually leverage the satellites and the onboard computing capacity, whatever is available on satellites, to actually improve the confidential computing requirements that these kinds of use cases are offering. In addition to this, there are several policy challenges, because right now there's a space race ongoing across the commercial companies, and not many people are investing in standards and optimizations and cross interactions. it's very likely folks like Starlink and OneWeb do not possibly participate in this because they are in here to make money. So it's likely going to be from the researchers, and more attention needs to be paid into this open problem as well. More coordination is also needed between folks like NASA, ESA, IETF communities, CCSTS, and so on, so that we can actually build a more cooperative space environment. To wrap it up, there are several pressing problems on this. We have a workshop associated with SIGCOMM, which is also going to come back again this year. The submission deadline is 1st of May. If you're working on any of these challenges, I highly suggest you to put in your papers to us. And we look forward to looking at your research. And with that, Debopam, take over.
Hey, Nitinder, thank you. Let me share my screen quickly. Can one of you please confirm if you can see my screen?
Yep.
Okay, all right. So hello, everyone. Let me start with a disclaimer that all opinions and content that I share in this session represent my individual views, not Microsoft opinions. Okay, so let's see how the 21st century gold rush is unfolding and how that relates to space. So, energy is really the new gold now. And many sectors, of course, need more energy. That's fine. But the AI data center demand is growing at an unprecedented rate. With a CAGR of 15 to 20%, the AI demand only in the US is set to surpass 1,000 terawatt hours by 2030, which is 2 times the yearly demand of Germany today. So globally, this is hundreds of billions of dollars of market. While demand is shooting up, supply side is ailing. Power grids are hard to expand quickly and could take years to sort out land issues and approvals. Deployments come with high capex, and long distance transmission is known to be very lossy. Currently, many grids are also going back on their sustainability commitments to cater to the growing AI demand. And this is getting reflected in the AI growth getting bottlenecked at times. And all the AI leaders are now highlighting the need to solve this energy problem. So the question is, how do we solve the AI energy bottleneck? And that too, preferably in a sustainable fashion. For completeness, let's touch upon a few terrestrial options first, as this is how we do it usually, right? So hyperscalers are setting up energy sources and large batteries next to large data centers, easing the strain on grids otherwise. Of course, this approach comes with challenges, and not all locations are suitable for such deployments. Large data centers are built on costly land, and installing energy sources could inflate this cost further. Strategically, an interesting approach could be to move compute closer to the existing sources of energy that are either curtailed or waiting in interconnection queues. The plot here shows grid interconnection queues growing over time, highlighting this opportunity. So, such modular geo-distributed deployments could generate local demand, and that too behind the meter before demand is onboarded to the grid. Supply is onboarded to the grid. And interesting research questions here include how to tackle the generation uncertainty and how to address remote maintenance and network connectivity challenges. The last terrestrial option I'll highlight is nuclear energy and small modular reactors for AI data centers. While nuclear energy offers high availability and stable supply, it could come at high capex, challenges in nuclear waste management, and associated risks that are involved. Now let's come to space-based solutions that are being explored right now, given solar energy is easier to capture in space. StarCloud is planning a centralized sun-synchronous data center in space with large PV arrays and compute and data shuttles for model training. There are many open questions though. What is really the break-even given the entire infra is now to be launched to space? How to efficiently tackle the data bottleneck for large model training? I know they're planning to send data shuttles to space, but this could be costly. How to deal with costly AI compute in a near zero maintenance environment? and how to effectively get rid of the heat that is produced because of all the computation that you are running in space. Many players, large and small, have recently announced plans to deploy constellations with AI compute. These include China's announcements, SpaceX announcements in the World Economic Forum, and Google's announcements too. Of course, there are many startups as well working in this space. While this is a good idea for Earth observation, data compression, and possibly AI inferencing, and a distributed constellation has better data uplink and downlink than a centralized deployment, model training is going to be hard over distributed AI infra. Also, millions of satellites with compute means the risk of Kessler syndrome could be significantly higher, and repairing is almost impossible. Finally, getting FCC approvals is getting harder every day as the space gets crowded. Interesting research questions here could be framed on training over a distributed constellation, and also the topology and trajectory design of such massive infrastructure in space. Finally, a potential hybrid solution is to beam energy from space using lasers and microwave, keeping AI infra-terrestrial. This is in early stages of research and limited demos, and there are many open questions to be addressed before there could be a commercial deployment. Having shared some potential terrestrial and space-based options to solve the AI energy crisis, I'll stop here. Thanks for listening and for giving me this wonderful opportunity to present in this forum. Thank you. Over to you, Deepak.
Hey everyone. Hope everyone can see and hear me. Shout out if not. I'm Deepak. I'm a professor in computer science in Illinois. And I'm going to actually not take a lot of your time because I know we're already running behind schedule and I want to leave a lot of time for questions. So today I just kind of seed one thought towards an approach that we've been taking in research in building for Earth and space. And then the core kernel of the idea is more focused towards, I would say, students in networking who are looking at what is different about the space, what are the kind of insights we can exploit to do research in this space, and specifically like even more focused on networking systems. So when we think of networking systems, they're typically designed to be reactive systems. And when I say reactive, like we measure something about the network, we assume like some form of like future, and then we react to that future. So this can be seen in data adaptation, ABR algorithms, congestion control, all of that. But the challenge is that things are moving really, really fast in these satellite networks, right? So LEO satellites move at about 15,000 miles per hour. And what that means is that if you end up measuring throughput for one of these networks, it changes a lot very, very fast. So past might not be as good of an indicator of the future in these networks. But we do have some hope that we can take actually a predictive networking approach to satellite networking. And what that means is that the physics of the orbits constrains how satellites can move. And now we have these like amazing machine learning capabilities that can add to that predictability. So we can start actually making better estimates of the future that do not just rely on past measurements, but also on the orbits that we see, as well as like other predictive patterns, for example, diurnal patterns in traffic demand, so on and so forth. And then we can use these predictions to enable efficient system design. And I'll give you like one example of what this means. So we tried, for example, I just showed you right that the throughput in a satellite network, this is again for Starlink, varies a lot even at the order of seconds. So the x-axis is only like 20 minutes in this case, right? And every few seconds it changes by a lot, and you can see the variation on the y-axis on the throughput. But we are able to predict that throughput by combining this understanding of orbital physics with machine learning very accurately. And once you can start doing that, you can think of like how would you adapt like everything else based on that? Like, can I design better ABR algorithms for video streaming using this insight? Can I think of better scheduling algorithms between space and Earth, both for the kind of Earth observation data that Nitinder like talked about, or so Debopam as well talked about, as well as networking data. And then can we think of distributed compute across Earth and space, and what kind of mechanisms that we can design for handoffs between them, given that the images being taken are predictive as well as the throughput is being predictive. So we've been to think of all of these questions. I'm happy to like chat more about this later in the panel, as well as like take questions on any of these topics. But these are the topics I work on.
Okay, I'm gonna try and share my screen. Talk about measurements. Okay, so all the panelists gave a number of very interesting research questions that we could work on. And the question is, how do we as researchers evaluate some of these proposals? Okay, and to look at that, maybe the best way to look at it is to kind of contrast with other sub communities within networking. So, for example, suppose I'm a data center researcher. How do I evaluate on my proposals? Well, I could buy a few racks of computers and then connect them together in my university and build my own data center, right? Now, if I'm a Leo networking researcher, so what does that translate to? Can I build my own constellation? There are research efforts that are trying to build their own constellations, but it's an extremely hard endeavor. There are big advantages. So for instance, if I'm working on Starlink's network or Amazon's network, these operators will not give me white box visibility into what is going to happen in the network, in the satellite. But if I'm going to build my own constellation in order to get this kind of visibility, I need to first find a launch slot. How do I find a launch slot in a very busy schedule already? Even if I manage to launch a few satellites into space, how can I compete with Starlink, which has nearly 10,000 satellites with inter-satellite links into space? Without such scale, I may not be able to replicate the emergent behaviors that you see in a large mega constellation such as Starlink, right? And even if I did manage to have a large-ish number of satellites in space, there are still issues such as the orbit that, as Nitinder showed, of Starlink is going to be at a particular inclination. Mine may not be in exactly the same inclination, so I may not be able to capture the specificities of currently deployed or planned constellations. So the proposals that I end up evaluating might not be runnable on a completely different constellation. So what's the solution here? I'll take you through a very short journey through some of the papers that we have published and try to generalize from that a call to arms for the research community. So when we first started looking at this with the first paper that did the measurement study of Starlink, this was in IMC 2022, the way we went about it was we created a browser plugin and invited users to start using it, right? And why did we do that? Because as an individual researcher in one university, I only have one vantage point, but I want coverage across the entire world because the performance in Australia might be different from the performance in North America versus the performance in Africa. So we managed to find coverage in some of these continents, but as you can see, a large number of continents did not have enough coverage. We also found that browser plugins are fantastic for coverage, but we don't have the fine-grained control that you would get from operating your own node. So in order to get this, we created a global testbed called Leoscope. Debopam is also part of that effort there. And what this gives us is very fine-grained control. And we have nodes in 5 different continents now, including Antarctica. Sadly, we don't have any in Asia or South America yet. Connectivity is still sparse in parts of North America as well. So you get control, but you lose some of the coverage. And furthermore, you're still operating on existing networks such as Starlink, and mostly it is Starlink because most nodes that you can find are Starlink nodes. So you cannot change constellations and change different parameters that Starlink has set for itself. So if you want the flexibility to look at new architectures, entirely new architectures, then you want a digital twin or a simulator. So we have built a big digital twin for this. And this helps, but it's not necessarily the same as an entirely deployed constellation, right? Finally, if you want both volume and coverage, then you can turn to some existing data sets, such as MLab. So MLab speed tests and Google NTT7 speed tests are published on MLab. And there's millions of these speed tests. There are also 70 to 80 RIPE Atlas nodes which run regular experiments behind Starlink terminals. And so you get the volume, you get the coverage as well, but you lack the flexibility to do your own experiments, even worse than what you can do with a browser plugin. So in some sense, we have these 4 different ways of doing research infrastructure, either using something like Leoscope, which is a global test bed, using simulation. So we have built Axioverse. Debopam had built Hypatia a few years back. Cosmic Beats is from Deepak. Browser plugins, Nitinder has done something called NetMet, which is also another browser plugin. There's public data and devices. So these are the kinds of infrastructures we have come up with, but we can't do this all just by ourselves as individual researchers. I'll use one example to show why. So we have a paper coming up in Sigmetrics in June, which is looking at the last 1.5 years of activity of solar storm activity, because we're in the middle of a solar peak, a peak of solar storm happening currently. To look at this, we need nodes in the high north, or also in the high south as well, in the down south as well, right? So near Antarctica and so forth. So we were able to do this mainly because we had some collaborators up north of Oslo in Simula Lab who were able to give us access to their Starlink node and also their OneWeb node eventually. And so we need a distributed setup. We need people to collaborate with each other in order to come up with these kind of things. So this is a call to arms. Leoscope and other research infrastructures need you. Please donate your nodes for Leo research. If you're a Leo researcher, you can also make use of existing nodes, but we would really highly encourage you to donate and your nodes as well to Leoscope. We really want to grow this, make it become something like Planet Lab for Starlink. So as a part of this effort and as a part of the larger effort to understand what research infrastructure exists, we started an effort in the Darkstool seminar, continuing this on within Space RG in IETF next week in Shenzhen. So this is a list of all the tools that are out there. If you have another tool that's here that you would like to see captured here, please use this QR code or visit this tiny.cc/space-networking-tools and input your information there as well. I'll stop there and hand it back to Jim for questions.
Okay. Well, that was just fabulous. Thank you all for those presentations. And I want to say to everybody that we'll be posting the presentations on the networking channel site, because there were lots of references and things that I think people would want to look at. And I guess I won't ask you when your report from Dogstool will be ready, but I'm sure a lot of people would like to read that. How will we find that?
So we are currently preparing this report, and Nishanth is also involved in this effort. Our estimate is it will take about a month or so, aligning between different participants.
Okay.
Yeah. So
Okay.
once this is out, we will post this also on the Sitcom
If
channel.
everyone is well behaved, then
Yeah, if everyone is well behaved, yes.
Okay. So we'll say 2 months, but because I think a lot of people in the community would be really interested in that. So place to go for additional information. We have a bunch of answers in the Q&A that I'm going to relay to you, but maybe I'll take the organizer prerogative here and ask you 2 quick questions. One of which actually came up in the Q&A, and the first is. Actually has to do about both of them have to do with changes over the last 2 or 3, 4 years. You'd mentioned the use of inter-satellite links, and I'm wondering the extent to which sort of the bent pipe up and down communication. With more data centers, you get better connectivity, so probably those decreased delays that you were talking about before, even in a bent pipe architecture. I'm curious about the use as opposed to the availability of inter-satellite links, say in Starlink. And I think one of you told me at SIGCOM that Antarctica is up and using inter-satellite links. Could you just informally say something about the use of inter-satellite links and doing that routing in space?
Yeah. So we have one node in Antarctica that was after a couple of years of talking to people in NSF Polar. And Antarctica is one of the few places where you do need intersatellite links because basically it's the easiest. Most of our traffic is basically to watch a Netflix or whatever, right? So if I'm able to go up, come back down, and then use the terrestrial internet, that's probably the simplest for Starlink and similar competitors. But Antarctica is so far away from every other landmass that you do need intersatellite links, and that turns out to be part of the difficulty to providing connectivity in Antarctica.
Nitinder, go ahead.
Yeah.
None of the panelists have to just start talking.
Okay. Yeah. So I can also build upon this. So ISL use specifically from Starlink perspective, we have been tracking this from with our longitudinal measurement studies. So before January of 2025, before the new point of presence was installed in Africa, all of the African customers were actually being mapped to Frankfurt point of presence. And this connection was over intersatellite links. This was also what we highlighted in our 2024 WebConf paper. And you could see that, okay, the link latencies are much longer. There's a lot of churn there as well. But we started to see that as 2025 new point of presence came in, the prerogative was to do the direct bend pipe. And the main reason why you do this is number one, your latencies, of course, decrease. So you are able to get to your egress point much quicker. That already gets you to an exchange point much faster. You get internet access services much faster. But the biggest challenge also is that if you are connecting to a point of presence which is in a different country or a different continent, you appear as a customer for that continent. So
Okay.
as an African user, if I'm asking for a content or web page, I will hit CDN servers, for example, in Germany, which will not cache my content, which means that I will come terrestrially to the root server and then get content back to Germany, which will then transport over satellite. So we saw this was a very bad quality of experience for African users, which have improved dramatically by several order of magnitudes after they have started to put point of presence closer to the users itself.
Okay. Great.
Okay, I will share probably a quick anecdote. So last year summer, I was traveling from Doha to Madrid to attend IITF, I think 123. So what happened was like on that airplane, I could connect to Starlink network. It was great bandwidth, decent bandwidth, like 50 megabit per second. But the trace route was very interesting. All the traffic was egressing in the US, right? And that is across the Atlantic. Right. So there as well, I think for many airlines, I think inter-satellite links are something that is used.
Great. I love geeks because only geeks would do trace routes while they're on airplanes and worry about where their satellite connections terminate. That's great. So another question related to changes in the past, and maybe I'm going to direct this specifically to Nishanth, since you had a paper in IMC 2022, I think that you may have mentioned, and there was a really interesting graph in there where you were sort of tracking on the same graph sort of distance to satellites, and you could see handoff, and you were looking at packet loss. So had to do with when handover happens in a satellite context where the same ground station gets handed off from one satellite to another, you could sort of correlate that with loss. I'm wondering if that problem has sort of gone away now with them being deployed, satellites being up there longer or with denser constellations, or is that still a problem?
I think it still exists as a problem, but probably to a lesser extent than back in 2022. Mostly density helps. The fact that you have many different satellites and you can switch between them helps. Also, Starlink specifically has a primary and a backup beam, so the switchover can be a little bit more transparent. So Nitinder's WWW 2024 paper also looked at how this handover actually happens on 15 seconds boundary. The predictive stuff that Deepak talked about can be used very effectively. And Debopam and I had a paper which is only on archive, which also looked at some of these predictive stuff as well. So we can
Yeah.
we can deal with it, but it's still a problem, right? And the variability of these links is much more than what we are used to in terrestrial settings. Even the loss, for example, so we get up to 5% loss easily, and that's almost unheard of in today's networks and terrestrial.
Yeah. Yeah, interesting about what you just said there about predictability. There was a conversation in the Q&A about predictability. I think it had a little bit more to do with routing, but this also, you'd mentioned sort of the handover aspect to that. So let me bring up a question that came up in the Q&A. This comes from Adisorn, who's at the Asian Institute of Technology in Bangkok, and was asking, and one of you made a comment about collisions in space or orbits in space and the FCC and things like that. So this is sort of a policy question. I think the question had to do with, well, whose job is it to sort of police space, if you will? One of you mentioned the FCC, but that's a US based institution. My understanding is that individual carriers have to actually, work with individual countries to get permission to do satellite into that country. So could you just say a little bit about, is there I don't know, is there some kind of global coordination about satellite policies for that, or is it done on an individual basis and sort of ad hoc? I'll just say ad hoc.
I'll just jump in. I think that's a very interesting question, Jim. I'll say to answer the second part of the question, there is this like entire field of like space situational awareness that kind of addresses this point in terms of the technology as well as in terms of policy. And then specifically, I mean, there's like FCC in the US, but ITU like globally, and then there's like other bodies that are kind of like actively working on this. And then in general, the way this works is that there are these very strict guidelines as to how close satellites can come to each other, and then they have to maneuver and have to have that ability, and also strict guidelines on what satellite, like how they will deorbit, and they'll not like hit your head, for example, when they come back to environment, so they'll burn on re-entry and all of that. So all of that is covered by both global and local policy. So there's like a lot of coordination on that. But my kind of personal, somewhat controversial take on this is that I do not really think that this is an urgent problem. And here is kind of one way to visualize this. That we have like Earth, right? Whatever the sphere, the surface area of the Earth, we have billions of cars. Each of these satellites is smaller than a car, and you have like 20,000 of them on a surface area that's much, much larger than the Earth. So at this point, I guess a lot of the work that we're doing on that side of things, on policy as well as space situational awareness, is more in preparation for when we have more satellites, or in the off event that we have one of these satellites break apart into like millions of pieces, and then it's like all around the orbit trying to run into each other, and that create this like kind of cascading effect. But as such, like space is very, very sparsely populated because it's like three-dimensional, and even if you take like a two-dimensional sphere around the surface of the Earth, it's like 4 times, or like tens of times the surface area, and then we have billion cars on Earth, and we're fine.
Okay, great. I'll point out that Matthias Halleck pointed to an ESA, European Space Agency document about protocols and tools to predict trajectories and prevent collisions. I noticed you said best practices, I've got to say. And so I always wonder, does anybody actually police that? And is there any regulatory body with teeth sort of equivalent to ICANN, for instance, for the wired internet or for the internet, that has policies that are somehow enforced? And I'm guessing it's more like a Wild West still, but I don't know. Because these seem to be recommendations and best practices as opposed to rules, or I get to say, or that organization gets to say, and therefore it's this way.
So
Please go ahead.
I can take this one. It is kind of a Wild West, especially from performance and operational perspectives. And this is all a black box on how the different LEO operators or even satellite operators are configuring the networks, which is why we started to look into exactly what's happening on trying to hack the system by measuring from outside. But the good thing about the infrastructure, unlike the terrestrial infrastructure, is that all of the information about which satellites are deployed, where they are running, what is their trajectory, is all open. So if you go to Celestrak, you can actually track the different satellite trajectories, and you can actually have the TLE data yourself, and you can see, okay, how Starlink satellites have been moving, deorbiting, and so on and so forth. This is something which is missing in terrestrial networks, where the infrastructure may be more obfuscated, but the performances are open. So there's a little bit of a mismatch in these two operations.
Okay.
Yeah.
So
And
I'll
then,
go next, probably. Just a
go
quick
ahead.
comment that things are going to get heated up even further So there are recent developments that happened. Starlink, SpaceX actually recently filed with FCC for an approval for 1 million satellites, and that too only in sun synchronous. So that is going to be very interesting, and there is a very interesting battle going on that. Other than that, I think I was reading a Google paper on Archive where they are also proposing, space constellation for AI, where satellites could be as close as 100 meters, right? So it's a very densely packed constellation that they're thinking of, and that could also be interesting in terms of collisions and triggering of Kessler syndrome.
So what we are also seeing is that Starlink and other satellites also have maneuverability, and in the paper that's upcoming with solar storms, we can see them actually maneuvering up and down. So maneuvering up to avoid the drag that's caused by solar storms and so forth. So they can kind of avoid it, but obviously there's a lot of debris out there. And there's also now capabilities that some state actors have to shoot satellites into tiny little pieces. And it can't be the best of things if you suddenly have little pieces of fenders or solar arrays or whatever coming at you when you're
Well, yeah,
traveling at
maybe we're going
27,000
back to the
kilometers.
early internet model of survivability being the most important thing. But
Possibly, yeah.
we're going to need to close in just a second. I want to just put out for everybody two comments that that are in the Q&A, mostly just so that people should be thinking about these things. One has to do with I guess I want to say the energy footprint or pollution footprint of data centers and satellites in general. And that's to think about the whole life cycle that is. So that yes, you can say, oh well, we're up in space and therefore, we can harness the sun and things like that. But then, there's launcher pollution and reentry, burn and things like that. And so I mean, even when you think about that in the US, like when I deliver a Netflix video, well, if you think about the manufacturing costs and the, full life cycle costs, it's just something to think about. The other question, and again, since we're pretty much out of time, I just want to put this up here. There was a question from Sumit Roy about no one's really talked about innovations or what's going on the individual sort of per link basis. And actually, it's pretty hard. I'll just say it's pretty hard to actually get data on that since the link seems to be pretty closed. And, I'm sure it's company confidential there. I'll say in reply to what Sumit posted, and Marie Jose Montpetit also posted that, there have been satellite links for 70 years, going back to Teledesic and even when none of you were even born when some of the first digital satellite links were up. Well, as you said, we're up there, right? And so there's been a lot of work in that area. Any comments on even where to go to sort of learn about advances in satellite link technology? From any of you?
Todd Humphreys in UT Austin did some very nice work looking at blind signal identification. And Oleg Gutkov, who has done amazing work in Ukraine at the border, trying to repair satellite dishes as they come to him. He has quite a lot of very interesting information on his blog as well. He was, by the way, one of the people featured behind Zelensky when Zelensky was Time Person of the Year. So go seek out his blog as well. Oleg Gutkov, Kutkov.
Okay, that's great. Okay. I want to thank you all again. Let me share a slide here, and then we can wrap things up. Can folks see that?
Yep.
Yes.
Yeah.
Yeah.
Okay, great. So I'm just waiting for my screen to clear here. I want to thank you all for being part of this. It keeps getting better every time. The last time we had a networking channel event on Leos, it was just absolutely fabulous, and this has been great too. So I want to thank all of you, and I'm sure and I'm sure many people here are sort of looking forward to continuing to follow your work and to take a look at your dog stool report as soon as that comes out. So thanks for all of that information. We'll post it. There's also an opportunity to continue the discussion on the SIGCOMM Slack, and I'm going to show where people can go to join that in just a second. I want to say that in 2 weeks, our next event, as you can see here on my screen, the future of paper reviewing, building a fair, sustainable system for the next decade for paper reviewing and the paper reviewing process. So I think that's going to be very interesting. Christophe Dio is organizing that, and you can see the folks who will be participating in that. And if you have more questions, you'd like to get more information, share perspectives, whatever, we have a Slack channel for SIGCOMM that you can see right there. And you can join that, post questions, engage in discussion. And then finally, I'll point out again, as I'm sure everybody knows, this video and all of the videos that we've been doing over the last 5 years for networking channel events are posted on YouTube and available through the networking channel site there, and also at networkingchannel.eu. Okay, so I think with that, we're all done. Thank you guys again. It was fabulous, wonderful to see you, and thanks for, again, a really great event here. Thanks.
Thank you.
Thank you so much.
Thank you.
Bye.
Bye-bye.